Hi, today we are going to solve a few problems using the commutation relations. Okay. All right. So first we'll start with this property of scalar products. All right. We are talking about operators here. So I may miss this hat at times. It's a bit difficult to keep track of these hats. So remember that we are talking about operators. So when we talk about vectors here in quantum mechanics, especially in this session, what I mean is actually vector operators. All right. Now we are supposed to show that a vector dot b vector is equal to b vector dot a vector plus the commutator ai with bi. All right. What does this actually mean? Right. Usually for normal vectors, you might have been familiar from everywhere else that for normal vectors, okay, a dot b is equal to b dot a. No problem, right? But we have said that operators in quantum mechanics are slightly different. They don't commute generally, okay? So if these are operators, right? Remember we are talking about operators, then we cannot generally say that a dot b is equal to b dot a, all right? If you are talking about operators, there is also an extra term ai with bi. And now how do we prove this? It's not quite difficult. It's quite easy. All right, but we'll have this formula because we'll be using it later on. Okay, so it's good to keep in mind, right? So a dot b, all right, a dot b, we write it as aibi. All right, again, as we have been doing earlier, we are using the Einstein summation convention. This means that the I is repeated here, so you have to sum over I. All right, a repeated index is actually a prescription to sum over. Right. So this actually means a1 b1 plus a2 b2 plus a3 b3. All right, that would be the sum over all possible values of I. Okay. All right. So remember that we are using Einstein summation convention throughout. Okay, throughout we are using that. Right. Now what do we have for ai with bi? Okay, what we have for here we have got ai bi and we need it of the form bi ai. Right. So let's look at ai. Let's look at the commutator ai with bi, and it is ai bi minus bi ai. All right, it's just the commutator. All right, so this means that ai bi here, that's equal to commutator ai with bi plus bi ai. That's it. Right, that's fine. So here instead of ai bi, what we do is it is bi ai plus commutator of ai with bi. And what's bi ai? Remember there was a summation. So this bi ai is nothing but b vector dot a vector. Right. So we have got b vector dot a vector plus commutator ai with bi. All right. Okay. Now we using this formula, let's show that r dot p is equal to p dot r plus 3i h cross. Again, these are operators. All right. We are not following. We are not keeping track of all the hats here because we said from the beginning that these are operators. All right. So these are r dot p is p dot r plus 3i h cross. How do we do this? It's quite simple. We know that r dot p, we use this formula. A dot b is b dot a plus commutator ai with bi. So r dot p is p dot r plus commutator ri pi. And what is commutator ri with pi? Right? You remember that this is one of the fundamental. This is the fundamental commutation relation in quantum mechanics. Ri with pi is delta. Actually, what we had earlier was ri with pj is equal to I h cross delta ij, right? I h cross delta ij, right? So ri with pi is I h cross delta ii, am I right? So this is I h cross. Oh, I missed an I h cross here. There's an I h cross there. So it's I h cross delta ii. And what's delta ii? Again, as we said earlier, we have started with the Einstein summation convention. That means that whenever this I appears twice, all right? Whenever this I appears twice, you have to sum over. Okay, so delta ii is actually delta 1 plus delta 2 plus delta 3. You have to sum over all possible values of I. All right. So what is this? This is 1 plus 1 plus 1, which is equal to 3. Okay, so delta ii is 3. Okay, because by delta ii, what we actually mean is I equal to 1 to 3. Okay, we are talking about 3-dimensional space here. Okay, so that's 3. So for this reason, r dot p is p dot r plus 3i h cross. Okay, again you might remember the correspondence I told you about. Okay, the correspondence between Poisson brackets and commutators. So if you know the Poisson brackets, you can get the commutators. All right. For example, we know the Poisson bracket Ri with Pj is simply delta Ij. All right. So the corresponding commutator, when you make them into operators, all right, is simply, this is Poisson bracket and this is the commutator. It is IH cos delta Ij. All right. So if you know the Poisson bracket, all right, you can get the corresponding commutator by getting rid of the Poisson bracket in favor of 1 by IH cross commutator. Right. So wherever you have a Poisson bracket, you change it into 1 by IH cross commutator. All right. So we will write the Poisson brackets like this. This is the correspondence. Whenever you have a Poisson bracket, you change it into 1 by IH cross commutator. Right, I've used curly brackets here for Poisson bracket, and that will give you the corresponding operator commutation relation. Right. Also, whatever is appearing here, you have to change them into operators. All right. Whatever is appearing in here, we have to write the commutator for the corresponding operators. Okay, I hope this is clear. All right. So if some Poisson bracket is 1 in classical mechanics, that means that the corresponding commutator, okay, divided by IH cross is equal to 1. Okay, I hope this is clear. Okay, we'll use this property because we are familiar with the Poisson brackets. We have done extensively, we have worked extensively on Poisson brackets, so it's easy to make this comparison. All right, especially when we talk about angular momentum, etc. It will be useful to remember some of the Poisson brackets that we have discussed in classical mechanics. Okay, so that's done. What do we have here? Showed that A cross B, the ith component, all right? You know that A cross B is a vector, so we are talking about the ith component of A cross B, that's equal to minus B cross A, the ith component of minus B cross A, plus an extra term here involving a commutator, all right? Normally for vectors, A cross B is equal to minus B cross A. This is for normal vectors, all right? But for vector operators, this is not generally true. Right? For vector operators, this is not generally true, all right? So when we do problems, there's always this temptation when you find something like, R cross L or something, there's a temptation to write it as minus L cross R, but you should not commit to that mistake, all right? I hope it's clear. When you have cross product, okay, when you have a cross product of two operators, right, two vector operators, when you have a cross product of two vector operators, when you shift the order of the cross product, you get an extra minus sign as usual and an extra term here involving the commutator. All right, so this is not very difficult to prove, nor is it very difficult to remember, but I want you to remember this. All right, this is a useful relation. This is a useful relation. Okay. Let's see how we prove this. Right? We have already said that if you have two vectors, all right, the ith component of it is given by if you have two vectors, the ith component of their cross product is given by epsilon ijk aj bk. All right, the summation over j and k, and we have talked about the Levi-Civita symbol in classical physics, so I don't think I have to repeat it here. All right, it's a Levi-Civita symbol. Just to refresh your memory, it has three possible values: 1, -1, and 0. It's completely antisymmetric about the exchange of any two indices. It's completely antisymmetric in all its indices, which means that if you interchange any two indices, you get an extra minus sign. Okay, and epsilon 1, 2, 3 in the cyclic order is 1. Right, you can get all the other values from. If any two indices repeat, then the value is 0. Okay, so here the summation is implied. Right, so this is an elegant and simple way to write down the components of a cross product. Okay, components of a cross product. Normally what you would do will be to write down the determinant and then find the components of the cross product, which may not be very effective. All right, when you solve problems, especially in angular momentum, etc. It's not always effective, it's not always efficient to write down the determinant and find the components of a cross product. Okay, so what we do is that we remember this and we follow this kind of index notation. It's much easier. Okay, you will see that it's much easier to manipulate. All right, so A cross B, the ith component is epsilon ijk aj bk. All right, so what is this aj bk? We can write it as bk aj plus aj comma bk. Am I right? Why? Because the commutator AJ with BK means AJ BK minus BK AJ. This means that AJ BK is equal to commutator AJ with BK plus BK AJ. Right? That's exactly what we saw in the previous problem also. It's not particularly difficult. So this epsilon ijk I have pulled out and written this AJ BK as BK AJ plus commutator AJ BK. Alright. Now what's this epsilon ijk BK AJ? What's epsilon ijk BK AJ? Alright. We know that if it's in this form, alright, if it is in this form, which means that the second index is summed over with the first thing and the third index is summed over with the third thing, alright, second vector, component of second vector, then we know that it's a cross product. So this is not exactly of the cross product form that we know, so we try to make it into a cross product form, alright. What do? If it's the k here and j here, then it's exactly in the cross product form. Again, here this j and k are dummy indices. You could use anything, the alpha, beta, delta, or anything. Okay, these are dummy indices. It's only a prescription to sum over. Right? So it doesn't matter whether you write j or k. The only important thing here is that the j appearing in the second place here comes comes as the index of the first vector here. Right? That's the only thing you need to remember. If it was a k here, and then it should have been a k there also. That's all. Okay, so it's a dummy index. So epsilon ijk bk aj can be written as, we can write as, we need to write it in the form of a cross product. So we write as epsilon I k j. So we say that epsilon ijk is minus epsilon I k j. Why? Because we said that it's completely antisymmetric in its indices. All right, the Levi-Civita symbol is completely antisymmetric in its indices. So what we do is that when we interchange these two indices, we get an extra minus sign. Okay? That's a property of this Levi-Civita symbol that we have been talking about. So it's minus epsilon I k j bk aj. What is this now? We know clearly that, see, there is a summation over the second index, or what do you say, second index here, and the kth component, the jth component comes here. So this is actually the ith component of b cross a. Okay, this is the ith component of b cross a with a minus sign here. Okay, that's what we have written here. It's the ith component of b cross a. Why? Because we know that b cross a, the ith component of b cross a is, we can write as epsilon I, let's say kj bk aj, or you could use any other index here. Okay, just have to use the same index here. All right. Okay, and then this term just carries over. It's epsilon ijk aj with bk. All right. So you will have this temptation. All right. People often make these mistakes, especially in problems involving angular momentum commutation relations. People often make this mistake and they completely miss one term. All right. So this happens often. So I don't want you to commit this mistake. Just remember. Okay. So if it's a cross product of two non-commuting vector operators, all right, if you are talking about a cross product of two non-commuting vector operators, then a cross b is not equal to minus b cross a. There's an extra term here. All right. So we can say that a cross b is generally not equal to b cross a. There are situations where they can be equal. One such situation is if these two vectors commute. All right. There are also other situations where the extra term will vanish. All right. There are situations where this extra term will indeed vanish, but generally you should be careful. All right. Generally a cross b is not b cross a. Okay. So let's check this. Okay. Show that L vector is equal to R cross B. Again, we are talking about operators. All right. I'm not keeping track of the hats. Remember that we are talking about operators. All right. So L vector is equal to R cross B is equal to minus B cross R. All right. Why shouldn't we need this extra term epsilon something? Okay. Shouldn't we need this extra term? Let's check. Okay. Let's check if that extra term becomes 0. Right. So first, this is a vector relation. So let's talk about the first component of it, or one particular component, the ith component of it. Okay. Let's talk about the ith component. So Li is R cross B, the ith component of R cross B. Okay. And this R cross B ith component, just by the previous relation, we can write as minus P cross R, the ith component of minus P cross R, plus there's this epsilon I. Okay. This I will come as the first index for the epsilon, and then jk, rj, pk. That's exactly what we saw before, right? See here, a cross b, the ith component of a cross b is minus b cross a, the ith component, plus epsilon ijk, aj, bk. It's not very difficult to remember. Okay, you have to remember this. It makes life easier. So, yeah, and what's RJPK? RJPK is IH cross delta JK. That's a fundamental commutation relation. All right, that's a fundamental commutation relation. It's IH cross delta JK. Okay, remember we are talking about Einstein summation convention. So, this means that there is a summation over J and K. There is a summation over J and K. This means that in the whole summation, the only term that survives is when J equal to K or K equal to J. Alright, so this is IH cross. So this becomes IH cross epsilon I KK, because the only term that survives in this whole summation is when J is equal to K. So you can write it as epsilon I KK. Okay, now here we have got two indices in the index of the Levi-Civita, which means that this is equal to 0 because it's completely antisymmetric. If any two indices have the same value, for if any two indices of the Levi-Civita symbol have the same, if any two indices are same, then its value is 0, right? Because it's completely antisymmetric. Okay, that's the reason why this term vanishes. This term vanishes, and for angular momentum, we can write. This is interesting. Okay, this is something special about this angular momentum vector operator in quantum mechanics. We can write as r cross p or minus p cross r. Both are correct. All right, both are correct. Okay, so it's something nice about this angular momentum operator. This angular momentum operator, you can, in this, for this purpose, you can simply treat it like normal vectors. All right. Okay. All right. Now, this Levi-Civita is very important. Okay, so let's look at some relations involving Levi-Civita, which will be useful in solving problems. All right. This identity is useful. Epsilon ijk, epsilon I pq. There's a summation over I. Okay, we are using Einstein summation convention. There's a summation over I here. There's a sum over I. All right. You see that this j, it's jk here and pq here. Okay, there's only a summation over I. Okay, so when you sum over I, it means that in the end you won't have any I index left. All right, you have summed it over. Yeah. So in the result, you will have only these indices j, k, p, and q. Okay, in the result of this, in the final result, you will have only 4 indices j, k, p, and q. Okay, now it's not particularly difficult to remember. This involves Kronecker deltas. All right, the answer involves Kronecker deltas. First, you take the combination j, p, and k, q. All right, which means that you combine the second index here with the second index here, and the third index here with the third index here. All right, so that's delta jp, delta kq, delta jp, delta kq. Right. Now what you do is that you combine this second index with the third index here and the third index here with the second index here. Okay, and for that you cost a minus sign. Right, for doing that exchange you get an extra minus sign. So it's minus delta jq and delta kp. Okay, so this is the case if any one index is the same. All right, especially the first index is the same. Okay. What if two indices are the same? What if two indices are the same? In that case, this is known as a contraction, all right? Because after we equate these two indices, we lose one index. You see that on the left-hand side, it seems that there are 3 plus 3, 6 indices, and on the right-hand side, there are only 4 indices, all right? That means that's because we say that this has been contracted. We have summed over that one, okay? So that's one way to check the consistency of an equation by looking at the indices. Okay, all right. So you can also think about something like this: epsilon ijk, epsilon ijq. Okay, epsilon ijk, epsilon ijq. Here, two indices are the same. Okay, you are summing over two indices. Okay, you are summing over both I and j. Right, and the answer is simply 2 delta kq. That's also not difficult to remember. Actually, you can prove this using this relation. Okay, you can prove it using that relation. Okay, so if the first two indices here and here are the same, then you are only left with two indices k and q, because other indices are summed over. Right, you are left with two indices k and q, and the result is twice delta kq. Okay, it's twice delta kq. All right. Now, if you can remember this, we can do the next problem. All right. The next problem might seem a bit complicated if we don't do it properly. All right. There are different ways to do that thing. Okay, let's check this thing. Find L square with R. All right. L is the orbital angular momentum. L is the orbital angular momentum operator. Orbital angular momentum operator. So orbital angular momentum operator. All right. Now, what's the specialty of this L? You might remember from Poisson brackets that if you have L vector with any vector, okay, pertaining to a system, let's say Li with Vj, something like this. All right. Then it's always, if it's a component of a vector and this is the angular momentum, then it's always epsilon I j k vk. All right, we have seen this. This is associated with the fact that angular momentum causes rotations. Okay, but this was not easy to. This is easy to remember, right? I hope you remember this Poisson bracket. We had talked about this extensively. Okay. Now, what happens when this commutator this Poisson bracket becomes a commutator? Only thing is you will have an extra IH cross here. All right. So this result, don't forget, for any vector. All right, for any vector L with, okay, this is a vector operator, let's say Li with Vj is equal to IH cross. There's an extra IH cross from quantum mechanical things. Otherwise, it's exactly same with the Poisson bracket relation. Okay, it's IH cross epsilon I j k vk. You have to remember this. Okay, you have to remember this. All right. So this is something that we'll be using in this problem. Right? Now we are supposed to find L square with R vector. Okay, L square with R vector. All right. Now how do we get about this? First we do is this. What we can write this L square as, L square is actually, what we mean by L square here is actually Li, summation over I implied. Okay, it's actually Li. This is L1 square plus L2 square plus L3 square, or you say Lx square plus Ly square plus Lz square. It's another way of writing it is Li. So we write as Li with R vector. Okay, here we have got a vector. So let's take one component of this and check, right? And we can generalize it to the other component. So we'll take an arbitrary component. We'll call it as Rj. Okay, we'll take it with the jth component of the vector. Right? You will see this is very simple. All right. Otherwise, the usual way that people do this problem is to write down these components of L vector, taking R cross P, and then find all those components and do this separately and do it. All right. But we don't have to go into that trouble if we can judiciously use this Levi-Civita symbol. All right. You can try it the other way. Okay? You can try it the other way. Okay? How do you try it the other way? This L square you will write as Lx square plus Ly square plus Lz square. Okay, and you know the components. You have to find the components Lx, Ly and Lz. Maybe you can do it by drawing the determinant and taking the components. Okay, and you find with some, let's say Rx, the components of R vector are x. Okay, you will also find it with y and z. Okay, this is what you have to do. Okay, you have to do it for each one, and then maybe you will see a pattern, maybe you won't, but it's much lengthier. Okay, the method that I'm going to give you here, it is much simpler. Okay, so I suggest that you practice this particular method. Okay, it saves you a lot of time. Just have to be a bit careful here. So let's do Li with Rj. All right, that's jth component of R vector. All right, some arbitrary component. Okay, we are not specifying which component it is. So this we use the usual rule. Okay, we use the usual rule. This is Li with Rj. All right, we know how to do AB with C. We know how to do AB with C. Okay, if you want to do AB with C, you do A with C and then put the B outside. Right? Remember, you have to take care of the relative position between A and B. B comes after A here, so it should come after A here also. Okay, there is also one more combination. There is B comma C, but you should remember that this A comes before this B, so this A comes here. Right? This is the relation. Okay, we use that here. This is A and B. All right, so you do it with both. This is Li. I've taken this combination first. So there is Okay, first actually I have taken this combination. So this Li comes on the left side, plus then I have taken this combination, and this particular Li comes on the right side. Okay, fine. Now we know Li with Rj. We know Li with Rj. It's IH cross epsilon ijk Rk. Alright, so we did not actually prove any of this, but we directly took it from the Poisson brackets that we are familiar with. Alright, we are already familiar with this Poisson brackets, so we have directly taken the result from here. We know how to convert the Poisson bracket to the corresponding commutator. Alright, so we can take that result directly. Okay, it's a good thing to have this connection in your mind. It makes things simpler, I guess. Right? So the only difference between the Poisson bracket and the commutator is that inside the commutator you have the operators for one thing. The other difference is that you have got an IH cross here. Okay, we discussed this. So it's Li IH cross epsilon ijk Rk. Why? Because R is a vector. Okay, so IH cross epsilon ijk, this is Rk. Alright, and the Li comes here. Alright, this Li, it's this thing. This Li is here. Alright, now these are numbers. Okay, we know that scalars commute with the operators, so we can write it like this. It's minus IH cross. Okay, why do I write it minus IH cross? Let me maybe write one more step here. This I can write as Li IH cross. Sorry, let me write it like this. IH cross epsilon ijk. Okay, I can bring this Li here, no problem. Okay, Li Rk. Alright, now we can write it in form of a cross product. You see that this seems like a cross product, except that there is some problem with indices. Alright, in which manner should we write the indices to get it in the form of a cross product? Okay, you see that whenever we have A cross B, ith component is epsilon ijk. Alright, the ith component epsilon ijk. Let's say A J B K, am I right? So in the same way, you see that there's a sum over I here. There's a sum over the first index and the third index. Alright, so it doesn't exactly look like the cross product that we are familiar with. So let's write it like this. This is minus IH cross. I just interchange these two indices and get a minus sign. Okay, so this is minus IH cross epsilon JIK LI RK. Alright, remember not to confuse the relative positioning of this, relative order of this LI and RK. Alright, that's one confusion that people make in this problem, and in the end one term will be missed out. Alright, we don't want to miss that term. So it's minus IH cross epsilon JIK LI RK. Alright, why is there a minus? Because I chose to interchange these two indices. Now what is this? We clearly see that this is the jth component. This is the jth component of a vector L cross R. Right? This is the jth component of a vector L cross R. That's what I have written here. This minus IH cross remains the minus IH cross L cross R jth component. Okay. In exactly the same way, what do we have here? Let's look at the second term. Okay. Let's look at the second term here. What do we have? It's IH cross epsilon ijk RK Li. It's RK Li. Okay. What do we do here to make it in the form of cross product? We need this J here. Alright. We need this J here, and also we need to write the K here. Only then it works. Alright. So we can write this term as just this is IH cross epsilon. First I'll interchange 1. Okay. I'll bring this J here. Okay, I'll bring this J here, right? Because the free index, whichever index is not summed over, we need first. Okay, that's the thing you need to remember. So the index that's not summed over is J. Okay, and then I write IK. Only by interchanging this, I got a minus sign. Okay, minus IH cross epsilon JIK RK LI. Okay, is this R cross L? No. Why? Because for R cross L, for the jth component of R cross L, we need epsilon JKI, right? This has to be summed over with the second index. So we do one more interchange and you'll get a plus sign here. That's IH cross epsilon JKI RK LI. Okay. Now clearly you see this index comes here and this index comes here. It's all correct. This is clearly in the form of a cross product. This is the jth component of R vector cross L vector. Okay. So IH cross R vector cross L vector jth component. Okay. Fine. So now let's try if we can combine these terms. Okay, let's try if we can combine these terms. So the normal temptation is to write it simply as minus IH cross L cross R. Okay, but we know better than that. We know we cannot write it. So we'll take this minus IH cross, this L cross R, okay, this L cross R, jth component, we'll write as minus R cross L, jth component, plus epsilon j mn rm ln. That's a relation that we saw before, right? We said that A cross B is equal to minus B cross A. Okay, let's say the ith component, okay, plus epsilon, okay, epsilon I, let's say jk ai aj bk, I'm sorry, aj bk, right? This is the relation that we saw already in one of the previous problems. So we just use that, all right? We just use that and write it like that. All right, now we see that we can combine these terms. All right, it's both are IH cross R cross L. This minus will cancel with this minus, so it's IH cross. So it's twice IH cross R cross L, the jth component. All right, that's what I have here. It's twice IH cross R cross L, jth component. Okay, there's another term here. There's another term here, don't forget. It's minus IH cross epsilon j mn rm ln. Rm ln. Okay, and what is this Rm ln? We already know from the Poisson bracket that this is epsilon m n, let's say I or some other dummy index, let's say k, okay, rk. This is epsilon m n k rk. Right? We already have this epsilon j mn here. So we just write it together. It is twice IH cross R cross L jth component. Okay, there's this minus IH cross epsilon j mn. That's what we have here, minus IH cross epsilon j mn, and then from the commutator you have IH cross epsilon mnk rk. All right. So there's an IH cross here, of course, because we are talking about commutator. Is this clear? I hope this is clear. Okay. Now what we have here, we have got this mn, jmn and mnk, right? Jmn and mnk. Also you see that there's a minus I here and a plus I here, so you can multiply and it becomes this h cross, it becomes h cross square. Okay. Now I just bring this k here. No. What should I bring here? It's epsilon jmn, epsilon jmn, epsilon mnk. Okay. So maybe I'll take this j here. Right. I'll take this j here. Then it's epsilon mnj, epsilon mnk. Right, epsilon mnj, epsilon mnk. All right, I'm taking j two places, so there will be twice a minus sign and there's no change to the symbol. All right, so why do I write like this? Because I already know this relation. Okay, I already know this relation. All right, what's epsilon mnj, epsilon mnk when the first two indices are the same and the third is different? Then it is simply 2 delta jk. Okay, it's one formula that we discussed just before some time. All right, you don't have to take the trouble of deriving it. It's easy to remember. Okay, if you have two index here and the same here, then there will be a twice, and there's the leftover index is j and k. It will come as the indices for a Kronecker delta. Okay, that's easy to remember. So it's this becomes h cross square twice delta jk rk. Okay, remember again there's a summation over k. There's a summation over k. So this means that for all this summation, the only non-zero value is when k is equal to j. That's what this Kronecker delta says us. Okay, so this summation is actually rj. Okay, so it's 2h cross square rj. So you see that this is actually the L square with r vector, the jth component of it. Okay, let's say L square with rj. This is just the jth component of it, but this is true. This is an arbitrary component. All right, for the first component, second component, third component, doesn't matter. It's the same. Right? So you can generally write L square with r vector is simply 2IH cross r cross L plus 2h cross square r vector. Right? R vector means you are just taking all these three components. This is only for one arbitrary component. So if you take all the components, there are three components. If you take all components, you will get the vector sign. All right. So it's 2IH cross r cross L plus 2h cross square r vector. All right. So if such a question has been asked in one of the previous examinations, and this was there in the option. All right. This was there in the option. That's the reason why we chose specifically to change this one to add it up, etc. Right? So you have to look at the options and find the answer. Right? Now, normally the mistake that people make is they'll miss this factor. They'll miss this particular factor, right? Because they'll miss this factor. That's a mistake that people usually make. All right? And to your disappointment, there will be an answer in the option without this factor. Right? There will be an answer in the option without this particular factor. And then you will see that answer, you will see that you got the same answer as one of the options, and you will easily choose that wrong option. All right. So the examiners know that you will make this particular mistake, and what they will do is they will include this particular option, this part alone in the options. All right. So if you miss this part, you will get this answer, you will mark it, and you will make a mistake. All right. So one thing to remember about this NET JRF exam is that it's full of traps. All right, that's full of traps. They kind of know what kind of mistakes students will make. Okay, and that mistaken answer will be there in the option, smiling at you and inviting you to mark that option. Okay, so you have to be careful here. So that's it. Now I leave it as an exercise for you to find L with R square. All right, we have found L with R. Now we need to find L with R square. So again, this R square you can write as Ri or Rj as you like. And you take one component of it and try the same thing. Okay, the answer is 0. Answer is 0. Now find the value of the commutator. This is another exercise I found. Find the value of the commutator x cap by px cap, comma px cap divided by x cap. Okay, x by px plus x by px, comma px by x. Okay, so what do we mean by this a by b? Okay, what do we mean by this a by b? So the usual convention is to write it as a b inverse, to write it as a b inverse. All right, this is not a good notation. Okay, this is not a good notation because it also, someone also might mistake it for b inverse a. Okay, someone also might mistake it for b inverse a. All right, but remember that it's a convention. If you have a by b, you write it as a b inverse. Okay, don't write it as b a inverse. Okay, so this is the thing that we use here. So you write this thing as x px inverse and px x inverse, and you do the commutator. You'll see that the terms will get cancelled. Okay, the terms will cancel and you'll get 0. Okay, you can try that. It's an exercise for you. You don't even have to use the fundamental commutational relation. You'll see that the terms go to 0 even before that. Okay. All right, here is another problem. Find e raised to x square, e raised to px square. Okay, e raised to x square, e raised to px square. So usually when we have e raised to a, e raised to b, we can write it as e raised to a plus b. Okay, but this is the case if a and b commute. This is the case if a and b commute. If they don't commute, there are some extra terms here. Actually, there's an infinite series here. Okay, that's known as the Baker-Campbell-Hausdorff formula, and actually you may not have to remember all these things, all right? You may not have to remember it completely, all these terms. I want you to remember at least these 3 terms, all right? At least these 3 terms. It's a plus b, of course. There should be e raised to a plus b, and then the next one will be plus half a comma b. There's also a commutator sitting here, all right? There are higher order terms, okay, which may not go to 0 always. In some cases, it will go to 0. Okay, because when you take a commutator, you may get a number, and then the commutator with the number will become 0, and all the higher order terms will become 0. Okay, so at least remember these 3 terms. It's e raised to a plus b, that's easy to remember. You already know that, plus half a comma b. Okay, usually if you do so much, okay, you will be able to isolate the correct answer from the options. All right, you can look at these 3 terms and then isolate the correct answer from the option. Now, if you are really keen, you can also study one more term. Okay, it's 1 by 12 a with a comma b. If you are really keen, you can study one more term and then remember this. Okay, in any case, you must remember at least up to this term. Okay, such questions are being asked for competitive examination. So if you do e raised to a, e raised to b as e raised to a plus b, obviously that answer will be in the options and you will get it wrong. All right, remember that there's at least another term here and possibly higher order terms. Okay, so this is the formula that I want you to use. Okay, and then you may have to use you may have to find the commutator x square with px square. All right, so you can use the formula that we studied. Maybe we can do it as x square with px first. Okay, you can do it. You can do x square with px first, and you can use the relations. This is a good exercise for you. Okay, this is a good exercise. So the first three terms are x square, px square, IH cross x px plus pxx. Okay, I think this is the answer. You can check. In the options, all right, you will see that in the options for this particular problem, it was given, this was the only option with the first three terms like this. Okay, so it was sufficient to remember up to this term in order to get this. Obviously, you cannot remember all the terms. All right, now if you are really interested, you can try to find what the next term is. Okay, whether it's 0 or if it's non-zero, etc. You can try to find the next terms also. You can also try to find if it converges. Okay, you can also try to find if it actually converges. Okay, I think it will converge after some time, right? I think it will converge after some time, means the higher order terms will go to 0, etc. Okay, so with that we can conclude this session. Okay, I hope you will get some more practice with these commutators. All right, so all the problems in this session have been selected in such a way that you get enough practice manipulating the commutators. All right, also this angular momentum commutation relations, etc. we'll use later on. We'll study angular momentum separately. Okay, and one minor point I wanted to tell you is in classical mechanics we said L with any vector. Okay, let's say Li with Vj. Okay, be it any vector pertaining to a system, it's epsilon ijk Vk. All right. Now, if it's a commutator, you just have to add an IH cross here and make these into operators. Okay, that's also fine. Now, this is true for all vectors except there's an exception. All right, there's one vector that does not obey this thing. All right, that's known as the spin. Okay? If this is the orbital angular momentum, then Li with Sj, if it's a spin operator, it's also a vector operator. This is equal to 0. Okay, you have to remember. So this is true if it's an orbital angular momentum here. If it's an orbital angular momentum here, okay, this relation is true for all vectors except for spin. Okay, for spin, the spin and orbital angular momentum will commute with each other. All right, it's except for spin. All right, spin also. So spin is something quantum mechanical. So we don't have this kind of Poisson bracket in classical mechanics. All right, we don't have the Poisson bracket between spin and orbital angular momentum, not in classical mechanics. Okay, this spin here is completely quantum mechanical. All right, so I just want to keep in mind the only exception to this rule is the spin. Okay, Li with Sj is equal to 0. All right. But if you take the total angular momentum here, all right, not the orbital angular momentum, instead if you take the total angular momentum, then you will see that, okay, we'll be discussing this in angular momentum. I just wanted to give you, what do you say, give it to you in advance, all right. If it's the total angular momentum, okay, let's say Ji with Vj, okay, this is any vector pertaining to a system. Right. In that case, this relation is always satisfied. It's IH cross epsilon ijk Vk. All right. Now, this is true if it's the total angular momentum. This is true also for the spin operator. Okay, just an information I want you to keep in mind. We'll be discussing this again when we discuss angular momentum algebra. Okay. Angular momentum specifically, we'll be discussing one whole module on angular momentum, and then you will come to these things. Okay, so I want you to remember this thing. If it's an orbital angular momentum, this is true for any vector except for spin. Okay, all right, with that we'll conclude this session. Thank you.